dimensions. If the object you're looking for is isotropic, you don't have to worry about making the section isotropic or the probe isotropic. I think that's a hard thing to prove in biology.
Sure. You can imagine an isotropic feature in like a marble. So a marble is perfectly spherical. You can imagine that no matter how that marble is presented.
So that jar of marbles we showed at the beginning, the distribution of those marbles would be isotropic. Let's take an organ like the brain. If you're talking about the organization of axons, in order to be anisotropic, that axon would have to, on average, come right back to the cell body. And that's not the way the brain is organized. And so most of the features we're looking at in biology, you can't assume that they're isotropic. So instead of assuming or proving that the particle or the feature is isotropic, we're going to either make the tissue isotropic or the probe isotropic.
Right. So you can achieve sampling isotropy in one of three ways. That object orientation, which we say, for the purposes of this talk, is a difficult thing to start off with. So you can design your experiment instead to achieve sampling isotropy either with your tissue preparation or with the probe itself.
Okay, so for the rest of the talk, let's assume that we don't know whether the objects are isotropic, so we have to assure isotropy some other way. One of the ways to do that is by how you section the tissue, and that brings us to this slide.
Yep, and there are three ways that you can prepare your tissue. You can create an isotropic tissue section, and in this case, all three planes are randomized using a 3D spin in the tissue before sectioning. So that would be analogous to that beach ball rolling up there in the upper right.
Okay, and the way this is practically done, one way you can do it is called the eye-sector. You actually take your little cube of tissue and embed it in a sphere of embedding material and roll it on the lab bench, and wherever it stops rolling, much like this beach ball is randomly rolling in all three directions, you pick it up and bring it over to your sectioning instrument, and it's a lot of times it's hard to see where your rostral and caudal and dorsal and medial are. So every time you see a beach ball in this presentation, it means that you have had to take the tissue and randomize it in three planes.
Another method is to section your tissue using vertical sectioning, and in this case, two planes are randomized using a 2D spin in the tissue prior to sectioning. So that's why we have the icon at the top.
The top spinning around, randomizing in two dimensions. A lot of organs kind of lend themselves to vertical sections because they have a naturally occurring horizontal plane. For instance, skin can be stretched out, and then you can take a piece of the skin and then rotate it randomly. That will randomize two planes of the tissue. That's a vertical section.
Right. And then the last option, which is something that is extremely common in neuroscience, is preferential tissue section. So this would be, for example, coronal, sagittal, transverse. In any case where you choose the way that the tissue is presented to the sectioning device, that is called a preferential section. So in order to use stereology, you need to obtain sampling isotropy with one of the other two ways, with the object or with the probe. So the reason why you would want to use preferential sections, especially in the brain, it's a very common situation, is because you need to know where we are. And, for example, you need to know where the caudate is in order to estimate the number of medium spiny neurons in the CP.
Sure, people have learned to read their tissue in a certain orientation, and many people want preferential tissue sections. For the rest of this talk, if you see a little icon with this atlas picture, it means that you can use preferential sections. If you see a top spinning, it means that you had to go through the trouble of randomizing two planes of your tissue section, and if you see the spinning beach ball, it means that you actually had to spin your tissue section, and so it's random in three planes. So, if you can't prove that your object you're looking for is isotropic, and you don't want to go through the trouble of doing the fancy sectioning, like the vertical or the isotropic sectioning, then what do we have to do?
Well, we have to make sure that we achieve isotropy using an isotropic probe. And so if you have an isotropic probe where the probe itself ensures that your feature is interacted with in all possible orientations, then you don't need to prove that your objects are isotropic or make your tissue isotropic.
Okay.
So an example example of a feature that would be isotropic would be planes oriented in 3 dimensions, like on the left, or a sphere. Yeah, before we move on, does anybody have any questions about this initial aspect that we've talked about before we start talking about which probes we recommend for each feature?
Okay, we have a question from someone who asks, can these techniques be used for lung stereology? So we are actually going to take each feature, the number, length, surface, and volume, and go through them one by one. Certainly you can use these stereology probes on any organ. I've noticed from reading the lung literature that many times thin sections are used in the lung literature. And so we are going to show you how to do these probes on thin sections. We're also going to show you how to do them on thick sections where you can use the probe itself to be isotropic. So we're going to show you an example of how to estimate surface in the lung on both. It could be used in the lung on both a thin or a thick section.
We also have a question about whether or not you need isotropy in order to do stereology. And the short answer is yes. You need to achieve isotropy in a combination of those 3 ways, either the way that the object is oriented within your organ or structure of interest, the way that you prepare your tissue needs to be achieving isotropy, or the probe itself has to have isotropy. Or you can reach isotropy, that randomness in the 3 dimensions, using a combination of those 3 things that we just mentioned.
And that's a good transition into the second part of the talk, where we're going to take each morphometric parameter and talk about the probes that we recommend, the easiest and most efficient ones, and how isotropy is achieved and whether you can use thick or thin sections.
Okay, so let's get right to it. Let's talk about number estimation first.
Okay, we definitely recommend a probe called the optical fractionator. This probe, when you're estimating number of particles, for instance, there's a picture of 36 cells inside of a volume. It's inside of a stack that's about 40 microns thick. You can see that this is a 3-dimensional volume, and we have particles in there. We need to use thick sections, and by thick I mean 20 to 40 microns thick. We can focus up and down through the Z-plane, and one of the rules of the optical fractionator is to find a unique point on the cell. In this case, we're using the top of the cell. So I'm not going through all the rules for the optical fractionator. We can help you with that. We have another webinar about that. But what I'm pointing out is that in order to focus up and down through many focal planes and find the tops of the cell, here's an example of putting a red dot on the top of the cell in the Z-plane, we need to use thick sections. But notice that if we rotate this block of tissue, and now instead of focusing through the Z-plane, we're focusing through the X-plane, so that what was the top of the cell is now the side of the cell, which is still indicated by the red dots. We focus up and down, and we look for the top of the cells, but from a different orientation. We're focusing up and down through the X-axis. Every particle still only has one top, and that's why the orientation of how you section the material does not matter when you're using the optical fractionator. So if you are estimating, notice how every cell, whether we came at it from the side or the top, each cell has either one red dot or one yellow dot. We've counted 36 cells, no matter how we've approached these cells, and that's why the optical fractionator is forgiving regarding how you can section the tissue. You don't have to use the vertical or the isotropic sectioning, and that's why we put this icon of an atlas picture in the lower left, which means you can section the tissue any way you want, the way you're used to looking at it.
Right, and the thick sections actually make it efficient too, right? But why do we need to compare the appearance of objects through a thick tissue?
Well, the reason you would want to use thick tissue and not thin tissue is so that you can have many optical planes and find the tops of more than one particle as you focus up and down.
So you think the tops are really important, right? And that's because of this. Probe counting is biased, right?
That's right. If you try to do this at lower power and you just looked at the profiles of these particles, the number of profiles would not relate in any easy way to the number of cells. So rather than counting cell pieces, we look for the leading edge, which we can call the top of the cell, and every cell will only have one top, whereas every cell will have more than one cell piece if you're counting pieces of cells.
Right. So from a single image plane, you can't come up with an accurate count of the number of objects.
You cannot. You need at least 2 image planes, and it's more efficient to do this in thick tissue and focus down through those image planes. But if you can't, but what if you have thin tissue?
So if you have thin tissue, we recommend a probe called the physical fractionator. And in this case, it's not sufficient that you have thin sections. You also need to have pairs of thin sections. They can be prepared in any orientation because the probe itself provides the isotropy, and the number is the output that you get out of this probe.
So we're still looking for the leading edge of the cells, but we're doing it with 2 physical sections. We look at the first physical section. If the profile is there but not in the second physical section, we know we found the top of the cell. Every cell has only one top, and we won't overcount cells, but we want to stress that this is way easier to do in a thick section optically than it is to get 2 thin sections, and by thin we mean something like 3 to 5 microns thick, rather than a thick section which is 20 to 40 microns thick.
Right. So any image analysis program would have to be able to find the top of the object in order to provide an unbiased answer of the number.
And that's easier to do in thick sections optically than it is to do in thin sections physically.
Okay.
What if you're working on the bottom of a petri dish, for instance?
In that case, you can use the fractionator technique. So in this way, you would do SRS sampling of a monolayer. This is going to be pretty familiar to people who do cell culture because it's very similar to how you would actually count the number of cells you're going to plate for your plating density using a hemocytometer. In this case, you're going to use the fractionator technique, so your isotropy is provided via the probe, and your output is going to be number.
Okay. So let's summarize estimating number with stereological probes.
So for the optical fractionator, you can have your tissue prepared in any orientation. However, those tissue sections should be thick. The optical fractionator is very efficient because it's much faster to focus up and down at any given sampling site than to do it on more sites on more sections, which is what you need to do for the physical fractionator, where you only have 2 planes that you're making a determination about.
So if you can get thick sections, you can use this efficient optical fractionator.
The physical fractionator is similar to the optical fractionator in that you can prepare your tissue in any orientation that you would like. However, you do need thin sections, and they must be paired.
An example of where you might need this is if you're working at the electron microscopy level, where you can't get thick sections.
Right. So if you're counting synapses, you might prefer to actually use the physical fractionator.
Pairs of thin sections.
If you are working in a monolayer, you can use the fractionator method, and in this case, there is no tissue thickness since the cells are associated in a monolayer.
So those are the 3 probes we recommend for estimating numbers of particles.
I want to just take a second and address a couple of the questions that have been coming in. You guys are great. We have a question about lung stereology. So that quite a few people who are interested in lungs, and that's fabulous. So when you have the situation that Ali is mentioning, where they have lung biopsies that are about 2 milliliters to be cut at 2 microns, can we use it for our samples? The answer is absolutely. When you have a biopsy, you have that opportunity to create isotropic sections, very straightforward, because you already have a piece of your tissue. And so in that case, you could achieve isotropy, sampling isotropy pretty easily by just isotropically sectioning your biopsy sample.
Of course, you wouldn't need the isotropy for estimating number, but do keep in mind when you look at a biopsy that you are only finding out about what's going on in the biopsy, and it's not necessarily representative of the whole organ.
Regina asks how thick or thin a section can be, and that's a very important question. when we talk about how thick a section should be, for the optical fractionator, for maximum efficiency and accuracy, we suggest that the tissue section be basically as thick as you can cut it, where you have staining that penetrates the entire section thickness. And so in practical terms, we'd be pretty happy if you could get a 20 micron post-processing section thickness or greater.
And in that case, you could use the optical fractionator, and of course you can use preferential sections.
Yeah, and then if we want to talk about thin sections, this idea of thin sections needs to be relational to the object that you're trying to estimate. And so for thin, you want to make sure that the object that you're trying to estimate has a chance of appearing in more than one section. And so for synapses, you would need, sub-micron range.
At the EM level, right? And that's one of the reasons why the physical fractionator is so difficult, because we're trying to get two physical sections that are closer together than the diameter of one particle.
We'll spend a little bit more time on the physical fractionator, and then we'll carry on. But there's what we mean by paired sections are sequential sections. So if you have your tissue sectioned at 2 microns and you want to count cell bodies, for example, that would be appropriate. And so you could take 2 sections that are sequential and then have an interval between the next pair of sections. And so when you're counting, you're actually counting what appears on section 1 versus what is no longer there on section 2 for each pair of sections through your systematic random series.
Yeah, and the reason you need pairs of contiguous sections is because we need to look in one section and see that the cell is there, and the next section and see that it's not there. Then we'll know that we found the cell top.
Right, and that's actually, when we talk about seriology, we want to get back to being efficient. And so the physical fractionator has specific applications where it is the most efficient method and accurate method for estimating number, for example. But we really recommend that you prepare your tissue where the tissue is cut thick, so staining penetrates all the way through, so that you can be more efficient and get your answer faster.
If at all possible, get thick sections and use the optical fractionator rather than the more difficult physical fractionator.
Yeah, and in this case, just one last point, those thick sections, when we talk about 20 microns, it's post-processing section thickness. So after you've actually stained the tissue and it's on your slide, we want a nice thick section.
And you can get a lot of shrinkage, especially with ascending alcohol concentration histology.
Yes, and so that has an impact on how you actually do your implement the optical fractionator. We have a webinar on that. I highly encourage you to visit our website and check that out if you'd like to learn more about the practical application of that method.
So these summary slides are kind of the take-home message for this webinar, and for number here is our probes that we recommend.
Okay. So let's move on to volume estimation.
Okay, so rather than trying to estimate the number of particles, now we're trying to estimate the volume of a region. And what you can do is use a method called tabulary with point passing. And your job, and again, we're marking an event. In the case of number, it was the top of the cell. Now we are marking a point if we see that point over our region of interest. So we have 4 plus signs on the right, and if I see the point is the vertex of the plus sign, if I see that point over my region, I put a green dot on it. Each point has an area associated with it. And so if I mark 4 points, I am telling the program that there are 4 regions of this type of area on my...
So you're representing each area by a single point.
Yes.
You're representing an area by a position of a point, and so it's a very straightforward way to get a quick estimate because you are making fewer decisions about the location of
Right, so you have this 3-dimensional solid, and what you do is you systematically and randomly section all the way through it. And now here's an example of one of those sections.
Yeah, and so you can see here that the grid is randomly tossed onto the region of interest, and you would mark as I did with these round circles, red circles, the points in which the grid points fall over my region of interest, which in this case is the red cortex.
It simply adds together the area associated with all those points and then multiplies by the distance between the sections to come up with an estimate of the volume. You can do this on thick or thin sections, so it's very forgiving that way.
And in any orientation. Because the isotropy is achieved via the probe, you can prepare your tissue any way you like. And so the estimate that I would get from a series of sections cut in the horizontal plane, measuring the right cortex, versus a series of sections that were cut in the coronal plane, measuring the right cortex, they would obtain a similar unbiased estimate.
In other words, it doesn't matter which direction we section up this region, we are going to get an equally unbiased estimate in either direction, so you don't have to worry about sectioning your tissue in any fancy way when you are using capillary point counting.
If you're interested in the component volume, so for example, plaque load in a neuroscience application, you don't necessarily want to have to sample at this high a density in order to calculate how much of the cortex is occupied by A-beta plaques. Instead, what we can use is a technique that drives off of the capillary point counting principle called the area fraction fractionator. So like the capillary point counting, we're going to use SRS sections that can be cut either thick or thin, because we're going to be operating on a single plane, actually.
We're putting these points down on a thin image, so we don't need thick sections to do this.
Yep, and they can be in any orientation. So the isotropy, again, is achieved via the probe, and your output is going to be a subvolume. So the amount of cortex occupied by plaques is a way of representing the data you will obtain using this type of probe.
Okay, let's summarize volume and cross-sectional area estimates.
So for capillary point counting, you can prepare your tissue and for sectioning in any orientation that you would like.
Great, so we don't have to worry about vertical sectioning or isotropic sectioning.
Not at all.
We can use coronal or sagittal or the way we want to section it.
And it can be any section thickness as well. It could be a single image plane, or it could be a thick or a thin section.
Okay, and the same goes for getting an estimate of the percentage of one type of tissue per another type of tissue, the volume ratio with the area fraction fractionator. So it's very forgiving when we're estimating volume.
It's very simple. You don't have to have a lot of forethought in your experimental design for stereology prior to actually sitting down at the scope to calculate the estimates for volume or area.
Okay, and when we estimated number, we could also go at it from any orientation, but we did have to worry about getting a thick section, so we could use the optical fractionator.
Yeah, and just a reminder, it's not one representative section that we're actually estimating for the area or volume. Instead, what we're doing is we're having an entire region of interest available for sampling, and then we're going to look and quantify the area on a systematic random sample of those sections through your region.
Okay, always use systematic random sampling. Okay, so now we've looked at number and volume. Let's turn to length and surface. Thanks for reminding me, Sue. Before we go to length and surface, let's look at the volume of particles. So we were just looking at regional volumes, and you may ask, well, why don't we just thoroughly section through the cell or the particle and do point counting on it? And that brings up one of the tenets of stereology, which is do more, less well. So we don't want to find out as much as we can about one cell. What we want to do is look at a group of cells and compare it to another group of cells. And so we're going to use the probe that, rather than sectioning exhaustively through the cell and doing point counting, we can throw down a line and see how the line interacts with the particle, with the cell. So we have the same group of 36 cells, and rather than finding their tops, I want to look at one of them, and I'm going to put a line down. I'm going to pick a random point in the middle of the cell, and then put a line segment down to the edge of the cell, and that's the red line there. So with this nucleator probe, we are actually taking a cross-section of the particle, putting a line down, then we take the length of that line and put it in the formula 4/3 pi length of the line cubed. So we get an estimate of the volume. Because we're working off a cross-section, if we approach the cell from another direction, we will get a different looking cross-section and a different length line. When we look at all the cells in our group, we don't want all the cells in one group to be cut along their long axis and all the cells in another group to, for instance, be cut along their short axis. So that's why we need to use a vertical section or an isotropic section when we do a local probe. We need to use thick sections because we want to pick these cells without bias to their size or orientation. So we're going to use a dissector, and a dissector, as we showed you when we were estimating number, needs to be put down in a thick section so you can focus through and decide which cells you're going to do the nucleator on. Then when you do the nucleator, it matters how the cells were cut. Therefore, you need to do this thing with the beach ball, where your block of tissue is random in 3 planes, or do a vertical section where it is random in 2 planes. And if you use vertical sections, you're going to have to show the software what the vertical direction is, because it's going to sign weight the line and make up for the fact that one of the directions is not random.
So what you're saying is that a combination of the probe and tissue, or actually if the object you are estimating you know to be isotropic, we have to achieve sampling isotropy in some combination of ways for the nucleator. The nucleator itself is not an isotropic probe.
Okay, so you're right about that. If you can somehow prove that the particles themselves are isotropic in space, and that's been done before, we can give you a reference in at least one region where someone has taken the trouble to do that, then we don't have to worry about being isotropic. But we don't want to cut these particles down their long axis every time or down their short axis. Therefore, we need to take the piece of tissue and make it isotropic for the isotropic nucleator, or we need to just spin that tissue to make 2 planes isotropic, and we'll make up for the other plane with the probe, and that's called the vertical nucleator. This is a rule that gets skipped or ignored a lot in stereology. You can always get something from your data. But this is probably the least forgiving of the probes, because we need to use isotropic sections or vertical sections, and we need to use thick sections.
And all of this is relevant because it depends on the population of the objects that you're trying to estimate. So if you don't know if they are isotropic, then you have to take pains to ensure that you achieve sampling isotropy with the probe and with the tissue preparation. As Dan mentioned, there are some reports in the literature of proving isotropy of a population of interest. There's a paper by Christoph Schmitz and Patrick Hoff that looks carefully at a population of cells in the striatum, I believe, in order to demonstrate that those cells themselves have no preferential orientation in the striatum, and therefore you can prepare your tissue with a preferential orientation for that region.
But if you don't know about your objects and you don't know that they're isotropic, then we need to use isotropic sections or vertical sections, and we need to use thick sections when we're probing for local volume.
Okay, so we've received a bunch of questions about this next topic we're going to cover, which is length estimation. Length estimation is of great interest for those people who are interested in blood vessels in particular, as well as fiber innervation. So if you want to understand whether or not a tumor has successfully recruited blood vessels to feed it, you can estimate the length of the capillaries to give you a metric for the invasiveness of that tumor, for example.
Yeah, so length is important to a lot of biologists, and this is a tree, a length tree. It kind of shows the historical progression of probes from the bottom to the top. So on the bottom of this tree are probes that are used. For instance, if you have isotropic tissue, and we're going to highlight that. So this is what we mean by this can be confusing, and we're going to try to demystify it. We're going to show you the 3 probes on this tree that we think that you can use for most situations.
Right. So again, these 3 probes that we're going to highlight we think are the easiest to implement and the most efficient and accurate way to get to your answer.
Okay, so if you don't want to prove that your object is isotropic, or you don't want to have to cut the tissue so that it comes out isotropic, like isotropic or vertically, the best thing to do is make the probe itself isotropic. So what we have here is it's something like a 60-micron thick stack of fibers. So we can see that this is a three-dimensional stack, and we are going to put a surface down into these fibers to estimate the length of the fibers.
Right, and the isotropic plane known as a sphere.
Yes, we're going to use a surface, and we're going to use, the surface is going to be the surface of the sphere, because the sphere itself is isotropic. This probe is called space balls. We need thick tissue so we can get the sphere in the tissue. Like I said, this is about 40 or 60 microns thick. You focus up and down, and wherever you see the fibers pierce the surface of the sphere, you mark that event. So I think we can see right here that a fiber is going through the sphere, and we put a pink dot on it. So here's one space ball, and every place, I think we're going to zoom in on this a little, we can see the fiber going through the surface of the sphere. The more intersections there are, the more the length is. There's a formula that will estimate that for you.
Right, and the blood vessel or fiber itself can pierce the sphere multiple times. And so long as it penetrates that plane of the sphere, you would continue to mark it.
And that makes sense. The longer it is, the more it's going to pierce. Don't forget that we're using systematic random sampling. So I've done 6 space balls here, but only one of them is showing. The more intersections you get, the longer your fibers are. So we're using thick sections so that we can use a probe that is itself isotropic, and that means we can use preferentially oriented tissue. What if you don't have thick sections? What if you have thin sections?
If you have thin sections, your options are a little bit more limited in that you need to achieve isotropy not with the probe, so you need to get it some other way.
Yes.
And so the most common way is with isotropic sections. So you prepare your biopsy or your sample of interest using the eye-center method. So you create it with an isotropic section technique, and then you can use the image plane itself as the probe.
So we're using a thin plane, and we're counting the intersections of the fibers with that plane that's shown on the bottom. Just like with the sphere, the more intersections you get, the longer the fibers are. But we need to make sure that this thin plane will interact with these fibers in the same way. And therefore, we have to take the tissue itself and make it isotropic, since the probe itself is not isotropic.
You don't know if the fibers themselves are isotropic. And in most cases, I think more so than cells, I think it would be safe to assume that most fibers do have a preferred orientation, even if they were...
Especially in the brain. A lot of times you're not going to know that, so use the thick tissue and use the sphere. The probe itself is isotropic. If you do use thin tissue, you have to make the tissue isotropic. That's why we have this spinning beach ball at the bottom.
So if you have a monolayer, the method that you can use to estimate length is a technique called petrometrics. In this case, you do get an isotropy via the probe, and the output is length. And so in this case, you would have a spicoid shape here that is presented across your tissue as in a systematic and random way, and you would indicate by placing a marker on each plane where the fiber crosses the probe itself.
So usually we use a plane probe for the length of the line, but because we're in a two-dimensional situation here, we can use one line to probe for the length of another line. I'm not sure if you guys can see these white lines inside of the counting frame, but there are these cycloid lines, and if you mark where the lines intersect the fibers, the more intersections you get, the longer the fibers are. Should we summarize the length estimation? Remember that complicated tree? We want to boil that down to just these 3 probes.
Yep, so Spaceballs is an isotropic probe that is used in thick tissue, and that tissue can be prepared or sectioned in any orientation that you prefer. If you have thin tissue, then you're going to be restricted to processing that tissue in an isotropic manner in order to be able to use an image plane as your probe. And then finally, if you have a monolayer, your option would our recommended option would be to use petrometrics.
Like if you're at the bottom of a petri dish, that's why it's called petrometrics. Okay, so let's turn to surface area, which is going to have similar concerns to length, in that we're going to need to make sure that the probe interacts with what you're probing for in an isotropic or a random way. And we're going to narrow down this kind of historical tree of all the probes that exist in a software to